In this example, we're trying to run a hypothesis test to determine whether or not the mean level of arsenic in a particular well is less than 8 parts per billion. 8 parts per billion is what is assumed to be naturally occurring amount of arsenic. So that helps us write the null and alternative hypothesis. Remember, that's the first step in making a hypothesis test. So the null hypothesis is that the mean level of naturally occurring arsenic is 8 parts per billion, and we're testing to see if the level of arsenic in this particular well is less or less than 0.8 parts per billion. Alpha, the level of significance of the test, will be 0.01. So there we've gathered the important information in step 1. Step 2 is to determine the appropriate test statistic. What will we need to do to run this test? You can read through the problem and notice that we are only given the sample standard deviation. We are not given the population standard deviation. Population standard deviation is unknown. That means that we have to run a t-test. We have larger than 30 in our sample size, so we can run the t-test without reservation. That means our test statistic will be a t-test statistic found by x bar, the sample mean, minus the assumed mean, divided by the sample standard deviation, divided by the square root of the sample size. By reading through this problem, you'll see that the sample size was 37. The mean of the sample, x bar, was 7.2 parts per billion, and the sample standard deviation is 1.9 parts per billion. So substitute that into this formula. We have x bar, sample mean, 7.2, minus the mean that we assume true in the null hypothesis, 8.0, divided by the sample standard deviation, 1.9, divided by the square root of the sample size, which is 37. All that stuff together in the calculator spits back a t-test statistic of negative 2.56. What is the p-value for this test statistic? We spoke about 2 ways of doing this in class. Either we can estimate it from the table, or we can use technology to tell us the exact p-value. Just to reiterate how to estimate the p-value from the table we're given, we first need to look at the said table. That will recall to our mind that we have a degrees of freedom. The degrees of freedom are 1 less than the sample size. In our sample, we had sample size of 37, which leads a degrees of freedom of 36. And our test statistic is 2.56. So we're going to try where the information overlaps in our t-table. So degrees of freedom were 36. The closest we can get there is 35. And we'll go over until we find 2.56. You'll notice that 2.56 is somewhere between 2.4 and 2.7. Now our t's test statistic, t equals 2.56, is between these two values. It's a one-tailed test. This is a left-tailed test. We want to find the area to the left of the negative of this t-value. So we're looking for the alpha prime number. We'll scroll back up to find what alpha prime is in between these two columns. So alpha 1 prime here is between, where our t is, between 0.01 and 0.005. That means our p-value of this test statistic is between 0.010 and 0.005. That means we can reject based on our given alpha, because the biggest p-value that we could get is at a number that's smaller than 2.56. So the number smaller than 2.56 from the table had a p-value of exactly 0.01. So this guy has to be something less than that. It's between the 0.01 and the 0.005, which means that the p-value is lower than the level of significance, and therefore we can reject. Alternatively, we talked about 2 ways to do this in a calculator, to use technology. A third way to do it is to ask Excel to calculate the p-value. One way we can do it is with the TCDF function, the T cumulative density function. You need to put in the minimum value, then the maximum value, and the degrees of freedom. In this case, we'll substitute a minimum of anything less than negative 2.56. In class we use like a negative 10. The max is negative 2.56, and the exact degrees of freedom are 36. Remember, to run TCDF, we need the distribution menu. Scroll down to find TCDF, cumulative distribution function. The lower bound of negative 1 e to the 99 is perfectly fine. Negative 10 will suffice, negative 5 would suffice. Anything far enough to the left, the upper value is negative 2.56, and degrees of freedom are 36. If you don't have the menu, remember you'll just put them in, separate the values by commas, press enter, and we find an exact p-value for this function, or for this test statistic, of 0.007, 4 to 4 decimal places. Again, that leads us to the same conclusion. If you check out the alpha, it's 0.01. In this case, the p-value is in fact low. It's low because it's less than alpha. Is low, less than alpha. So we would reject, again, the null hypothesis. If you want to run the whole test in the calculator, we can do that as well. Also in the stat menu, so let me get out of here. The stat menu allows us to run tests. We also were able to find intervals in here. We're running a t-test, number 2. We're going to put in summary statistics, so highlight stats and press enter. The null hypothesis, mu naught, is the thing we assume to be true. That was 8.0 from the problem. X bar is the sample mean, 7.2. SX, the sample standard deviation, 1.9. And N, the sample size, is 37. We do have to tell the calculator what type of test we're running, left-tailed, right-tailed, or two-tailed. That's the statement that's in the alternative hypothesis. We found here that this was a left-tailed test. We were interested in the probability that it's less than 8 parts per billion, so highlight the left-tailed business, the less than null hypothesis, and then press calculate. And that can help us verify our information and give you the alternative hypothesis, the test statistic, negative 2.56, which is exactly what we had by hand, p-value 0.00738, still 0.00734, rounded to 4 decimal places, and then the mean, the standard deviation, and the sample size are reiterated for us just to verify that they are in fact what we thought they were, and kind of give you a check that you put the information in correctly. So remember, that was by running the t-test with the given information, and that gave a p-value of 0.0074. So no matter how you slice it, the conclusion is to reject the null hypothesis. We can say that there is sufficient information from the sample to support the claim in the alternative hypothesis that the mean level of arsenic in this well is less than 8 parts per billion. More likely than not, when we are faced with real-life situations where we want to run a hypothesis test, we'll be given a bunch of raw data, and that's what we have in this example, just a list of information. So the list here is the hemoglobin count in grams per 100 milliliters of whole blood. We see that the distribution is approximately normal, and with a population mean of about 14 for healthy adult women. The patient has taken 10 laboratory blood tests during the past year. The results are here. And our test, or the thing we want to run is the population average for hemoglobin count for this particular patient more than 14 at a level of significance of alpha equals 0.01. So first we need to set up our null and alternative hypotheses. The null hypothesis is that this patient is average, that the mean hemoglobin count for this patient is 14 grams per 100 milliliters. The alternative hypothesis is the thing we're trying to find evidence to support. Is it really the mean hemoglobin count for this patient really larger than 14? And we're going to run that test at a level of significance of 0.01. Second, we need to determine the test statistic. What distribution is this? We only have raw data. If we only have raw data, we have nothing about the population standard deviation. We do know that the distribution of X is approximately normal. And so even though we have a small sample size, which was 10, because the distribution is approximately normal, it's okay for us to use the t distribution. So that means we're going to calculate a t test statistic, x bar minus the mean, divided by the sample standard deviation, divided by the square root of the sample size. Now, one thing you might notice is that there's no value of x bar given, no value of sample standard deviation given either. Instead, we have, again, raw data. So this is where students either completely forget what we talked about earlier, or they start to remember that because we're given raw data, we can calculate these values on our own. We can do it by hand, add up all the values, and divide by the total number of values provided. Find the mean, subtract the mean from every individual data point, square that difference, add it up, divide by the sample size minus 1, and then take the square root for the standard deviation. But no matter what you do, you're going to have to get those values to move forward. So one easy way to do it is put it in the calculator. We learned earlier this semester a way to calculate the mean and standard deviation by entering the data into the list by pressing stat and the first number 1 edit. We can enter this information into the list. So there's 15 is one result, 18 is the next, then 16, then 19, then 14, 12, 14, 17, 15, and 11. Sure enough, that's 10 entries, and that was our sample size, so that's good news. You can quit from there and run the one variable statistics with stat calc one variable statistics on list 1. To calculate that, we have a mean of list 1 of 15.1 and a standard deviation of 2.514402955 if I write down all the values the calculator gives us. So now if we know x bar and the standard deviation 2.514402955, we can calculate this formula, right? X bar 15.1 minus the mean we assume to be 14 divided by this large standard deviation divided by the square root of the sample size can give us the value for the test statistic. The next step would be to find the p-value of that test statistic, and then lastly decide what to do. Do we reject the null hypothesis or not? To find the p-value, we said we could estimate it from the table, or we can ask technology, and if we're going to ask technology for the p-value, we might as well see what technology has to say about the sample test statistic as well. Running the test, we go to stat, tests, and scroll down to t-test. Now instead of entering summary statistics, we could just run it directly from the data. That allows us to sort of skip this step because there's no reason in going here. If you're going to ask the calculator to run the test anyway, we don't need the mean and standard deviation. I put the list in the data, highlight the data, press enter, enter the null hypothesis. Remember that was 14. The data is in list 1, and we are running a right-tailed test to see if this patient has a higher hemoglobin count, and we can calculate from there. So this one is quite a bit more direct method. Gives the test statistic right away, 1.3834 to 3 decimal places, 1.383. The p-value is 0.0999, And then the summary statistics are given there, 15.1 and 2.5144 with a sample size of 10. Again, just for confirmation, or should you need those for another problem, they're there. They needed to calculate it anyway to run the test, so we might as well get the information as well. Once we have the p-value, we can make the decision. So remember, the p-value is 0.0999. We want to compare that p-value to the alpha, the level of significance, 0.01. In this case, which one is smaller? The question is p less than alpha? Is the p-value low? One way to compare two numbers is to line them up, 0.0999 compared to 0.01. And we can go through and compare digit to digit. So start on the left, 0 and 0 are the same, 0 and 0 are the same. Then we're comparing 9 and 1. And you see that 9 is larger than 1, therefore this number is larger than the other number, which means that 0.0999 is not less than 0.01, which means that we fail to reject the null hypothesis. So although this patient had an average hemoglobin count of 15.1, that was higher than 14, what we assume to be normal, it's not high enough for us to claim that the average hemoglobin count for this patient is more than 14. You can see that she had some times that they were less than 14, sometimes that they were exactly the typical average, and then there were some other times where it was higher. So based on this test at a level of significance of 0.01, there's insufficient evidence to conclude that the hemoglobin count for this patient is more than 14.